Arguably, climate science, at least modern climate science, post-Aristotle, begins in France with the French polymath Jean-Baptiste Fourier. And those engineers in the audience will be familiar with Fourier's series. This is the same chap. He was the first to really understand that the Earth's atmosphere provides something like a greenhouse effect, that the surface temperature of the Earth would be considerably colder than it actually is because of the atmosphere. He didn't quite understand what it was about the atmosphere that caused that, and that was left to the great Irish physicist John Tyndall, whose dour portrait you see up there on the right, who built the apparatus that you see at the bottom of this slide for very carefully measuring the passage of electromagnetic radiation in different wavelengths, covering both solar and terrestrial infrared radiation, through various gases that he could control. And Tyndall made a very remarkable and deeply disturbing and counterintuitive discovery about the way the climate works. And that, in a nutshell, is illustrated by the sort of pie chart here. He looked at the composition, of course, which was well known by his time, the late 19th century. As you know, most of our atmosphere is comprised of molecular oxygen and nitrogen. Together they make up close to 99% of the atmosphere, also argon. And Tyndall's remarkable discovery, and this defeats a lot of people today, this idea, is that those gases basically are completely transparent, both to solar and infrared radiation, just go right through it. Okay? That the fact that we're not living on a snowball is owing to the presence of trace constituents, which are represented by the orange slice that you see, that you might see on this pie chart if you've got good eyesight and you're sitting in the front. Okay? So water vapor, about 0.25% of the mass of the atmosphere, carbon dioxide, about 0.04%, and a few other trace gases, are responsible for the difference between a snowball and our current climate. Okay? That's a really, really interesting finding. And the intuition you develop about that is that some of those greenhouse gases, at any rate, must act as kind of a regulator, that they themselves are tightly controlled, because if they weren't, we would have really wildly fluctuating climate. Now, water vapor, which is most of the greenhouse effect in our atmosphere, it absorbs, and the other greenhouse gases absorb infrared radiation radiated by the surface, and re-emits that radiation both up to space and back down to the surface. Remarkably, over the course of a day averaged over the planet, the surface receives more than twice as much back radiation from the atmosphere and the clouds within it as it does directly from the sun. That's how powerful the greenhouse effect is. All right? And that was really Tyndall's discovery. But water vapor is a bit different because it's regulated mostly by temperature. It responds very quickly to changes in temperature, and therefore we have to consider the feedback. The actual regulation is done by carbon dioxide, methane, and a handful of other gases that if I put on that pie chart, you wouldn't be able to see even if you were sitting in the front row with a telescope. One of the next advances was made by this unhappy-looking Swedish chemist, von Arrhenius, a Nobel Prize winner. What is it about climate scientists that they look so unhappy? I can assure you the ones I work with do not have these sour dispositions. They're all very great people here at MIT. But Arrhenius is credited for as being the first scientist to understand that mankind could, and probably was, changing the composition of the atmosphere, changing the greenhouse gas content, and because that was so small, we can have an impact on it, and that could change the climate. And he was the first to make a prediction. He recognized that the combustion of fossil fuels would lead to an increase in gases like carbon dioxide, and he predicted that if you doubled the carbon dioxide concentration of the atmosphere, that the Earth's surface temperature would go up by about 4 degrees centigrade. Okay? Now, that's a remarkable prediction because more than a century later, armed now with supercomputers, very, very good measurements, satellites, and so forth, the latest estimate that scientists have been able to make, put the range of probable increase due to doubling of CO2 at between 1.5 and 4.5 degrees. And this guy did it with paper and pencil more than 100 years ago. So one of the things that's important for you to recognize is that climate science, and indeed the notion that we're changing climate, is nothing terribly new, okay? Arguably, Arrhenius' prediction has been borne out by observations. And what you see on this chart is a history of the Earth's surface temperature going back to about 1880. That's the green curve. And you see that it's basically increasing, but there's also all kinds of interesting variability. There's chaotic variability. There's variability due to other influences like volcanic eruptions and so forth. It's a really fascinating system to climate. And this, by the way, is something that gets lost in all the publicity about climate change. And I'll come back to this theme in a bit. It's a very, very interesting problem intellectually, even if we weren't changing the climate. It's all full of all kinds of interesting science. But there we have that. The blue curve is proportional to the natural logarithm of the carbon dioxide content. And theoretically, the radiative effects of carbon dioxide scale with their log. That's why I've used that. And you can see that the idea that carbon dioxide has something to do with temperature is pretty well borne out by observations. Of course, the case that is based on a lot more than the information you see in this graph. But there have been other sort of stunning successes in climate science that have nothing to do particularly with the problem of global warming, and also have a fairly old lineage. So here is a Serbian mathematician, Milankovic, who lived from the end of the 19th century to the middle of the 20th century, who had the idea that ice ages, and by that time it was pretty well, by his time it was pretty well known that the Earth went in and out of these glacial episodes for the last few million years, roughly every 100,000 years or so, might be paced, or in some sense caused, by perfectly periodic, almost perfectly predictable variations in the Earth's rotation about its axis and in the Earth's orbit around the Sun. And today we call those periodic variations Milankovitch cycles. They're caused by the influence of the Moon and other planets on the Earth's orbit. And he was able to characterize them very precisely. And one of the great successes in the field of climate has been in the field of paleoclimate. You're going to hear a little bit more about that later this morning. But paleoclimate evidence has really borne out Milankovich's predictions, which, by the way, in his lifetime were thought to be somewhat crazy. So here is some really interesting evidence. There are two curves here that go back. If you read this chart from left to right, this is time in thousands of years ago, so that left-hand corner is 1 million years ago. And there are two quantities plotted. One is, according to Milankovich's mathematics, basically the radiation absorbed north of 60 degrees north over the course of the summer. That's the red curve. The black curve is the time rate of change of the ratio of two isotopes of oxygen in deep sea sediments. And that ratio actually tells us rather precisely what the volume of ice is on the planet. All right? It's a remarkable thing. I don't kind of go into the chemistry and physics behind that. But you can see how well those two curves are correlated. This is, I think, a vindication largely of Milankovich's predictions. So there have been some very interesting successes in climate science. And this paleoclimate field is very rich and interesting. Here is a record going back 450,000 years of temperature as inferred mostly from these oxygen isotope ratios in ice cores and in ice volume, which is inferred by the chemical composition of deep sea sediments, and you can see how well correlated these records are. So we've got a pretty good idea now, although it's not entirely solved problem, of why the Earth has gone in and out of ice ages over the last few million years. We also can look at bubbles of carbon dioxide and other gases trapped in ice cores, and here's a record going back to 900 AD of the carbon dioxide content, and also compared to actual direct measurements, which began in Hawaii in 1958 in the black circles. And you can see that the CO2 content has been very stable, was very stable at about 280 parts per million. through about the very beginning of the 19th century, and then shot up. And if we go back, I don't have the chart that shows that, but we can go back many, many thousands of years, actually hundreds of thousands of years. This rate of change in carbon dioxide we have not seen on this planet for a very, very, very long time. That's the source of so much concern about what's happening with climate. Now, besides paleoclimate, we have models, and we have models ranging up from very simple ones. I'm showing you the results of here that our students can develop and run on laptops, all the way up to supercomputer models where you have to call a power company before you turn them on, and so forth. But the simple and complicated models for quantities like the global mean surface temperature are quite consistent with each other. So here's a bunch of experiments, and what you see on the bottom axis is the number of doublings of carbon dioxide. Remember, its effect goes up logarithmically. And then the mean surface temperature on the vertical axis. And you can see that the average slope of this line is about 3 degrees surface temperature per doubling from the simple model right in the middle of the IPCC range of 1.5 to 4.5 degrees. Now, the crux of the problem going forward is sort of given by a graph like this, which is made from the output of lots and lots of different simulations with various models. And it is showing basically the probability of surface warming owing to doubling of carbon dioxide. So on the bottom axis is global mean surface temperature again. And on the axis is sort of the probability, on the y-axis is the probability. And there's a lot in this graph that causes us to think very carefully about the problem. The most probable warming due to doubling of CO2, by the way, we're going to do much more than double CO2, quite clearly, we as a species, is somewhere in the range of 2 to 3 or 3.5 degrees. But there's this disturbing tail out there beyond 4.5 degrees or so. And if you start to look at the consequences, and President Reich told you a little bit about that, of this, they really start to get very severe out at the end of this tail. And one of the many consequences that we're worried about is water and food shortages, which tend historically to lead to ugly things like armed conflict. And these are the real risks associated with climate change. But there are others, like extreme events, hurricanes, and so forth. So that is, in a very quick nutshell, a tutorial on climate. That's kind of where we're at. It's obviously a much richer story than I have time to tell you about now. But I want to turn the page now and talk about what I view and my colleagues view as MIT's special role in it. I mean, as President Reich told us all, we do have a special role in informing the world and trying to solve its problems. And MIT has been active in this. And for example, Professor von Prien for several decades now has run MIT's Center for Global Change Science and Policy, which brings scientific knowledge to bear on solving real-world problems. How do you actually deal with this? But MIT has also started much more recently some new initiatives, and that's what I want to talk to you about a little bit. Just a few weeks ago, we announced a big institute-wide initiative, which Rob Van Hilst mentioned to you, called the MIT Environmental Initiative. It's headed by Susan Solomon, one of the world's greatest climate scientists, who came to MIT just a few years ago. And the goal of this initiative, and it is across the Institute, is to promote research that engages wide participation by members of the MIT community to address the most significant interdisciplinary problems in our environment, spanning the physical and social sciences, engineering, and urban planning and policy. Now, the word interdisciplinary is used a lot. And in the framework of climate, it really is interdisciplinary. It's a very complex system, especially when you throw in the human elements that control things like emissions of carbon dioxide and the response of civilization to climate change. This requires a new approach that spans across departments and groups, and this is what we hope to accomplish. MIT actually historically has been very good about tearing down intellectual boundaries between disciplines. The goal of the initiative will be very specific for faculty members to self-organize into teams of people who are interested in defining genuinely new research directions, to come up with ideas across schools, and to propose research that might not easily be funded by current federal agencies, which tend to be defined by disciplinary areas. So those are attempts to further break down some of these barriers. Now, as Rob mentioned, Dan Rothman, my colleague in EAPS, and I co-direct an effort that was started a few years ago called the Lorenz Center. And that is directed at the first of the two MIT goals, which is to understand the world, basically. This is something that is necessary before you actually start solving problems, is to understand them. And in the case of climate science, there's a general sense that our tendency to want to solve the problems has run out a little bit ahead of our actual knowledge base. And it's the aim of the Lorenz Center to try to go back to fundamentals on climate science to establish the knowledge base that's necessary to start solving some of these problems. And we believe that the intellectual challenge of climate change is perhaps the most complex such challenge that humans have ever faced. And what better place to attack that problem than here at MIT? Simply put, our idea is to try to attract the very best minds in science and give them free rein to think creatively, unsaddled by the pressing practical demands of forecasting climate. So the world's desire to have answers, in some sense, as I mentioned before, has run out ahead of our ability to provide them. And it's our attempt to say, let's go back to basics. Let's create a really exciting environment that will attract the best young minds to think creatively about the climate and actually try to pin down the understanding so that we can make advances. So the emphasis is on fundamental questions. For example, is the Earth's climate, is there only one statistical equilibrium for a given forcing? If we started the Earth, if we could start the Earth in a different initial state, would it eventually attain the same climate or a different climate? It would seem like a very obvious first thing to solve, and yet we don't really know the answer to that question. There's lots of indications now that there are multiple stable equilibria for the same sunlight, the same atmospheric composition. Why does carbon dioxide go up and down in temperature during the ice ages? That's very well established by paleoclimate data, but we don't really know why that's the case. And what causes the deep circulation of the ocean? A really fundamental problem, because the ocean transports a lot of heat. It's questions like that, fundamental questions, which may or may not have anything to do with global warming. They're just interesting questions that this center tries to attack. So that is the end of my tutorial on climate, and I'll be interested to talk to you later